Okay, guys, so today we're going to talk about kinetic molecular theory. And basically, what kinetic molecular theory allows us to do is to compare or to look at the actual speeds or velocities or kinetic energy of the particles within a gas. So it kind of gives us more of a microscopic view of gases. So the simplest model for the behavior of gases is the kinetic molecular theory. In this theory, a gas is modeled as a collection of particles, either as molecules or atoms, depending on the gas, in constant motion. So we're looking at a gas as a collection of particles constantly moving. So there are several assumptions when talking about kinetic molecular theory. And again, these have to do with our view of the particles. So the first one is the volume of a gas particles can be assumed to be negligible relative to the space between them, meaning that the actual size of the molecules does not necessarily matter when talking about the volume of the gas overall. Now, we're going to look at this a little differently next class when we're looking at the behavior of real gases. But just understand that for the kinetic molecular theory today, that the size of the particles does not matter because that space between them is just so large. The second postulate is the average kinetic energy of a gas sample is directly proportional to the temperature of the gas in Kelvin. And we're going to look at that, how kinetic energy and temperature is directly related. And notice it's the average kinetic energy. Okay, so keep that in mind. The third one is gas particles are in constant motion. Gas particles colliding with the walls of their container are completely elastic and produce pressure. So we're going to look at what elastic means and how that works. And then the fourth one is gas particles neither attract nor repel one another. So that means that even when they collide, so like over here, they are colliding, even when they collide, those intermolecular forces are not going to take over because the actual kinetic energy of both of those particles is much higher than the attraction for the intermolecular force. Okay, let's look at two of these postulates a little more in depth. So, first one is the average kinetic energy of the gas particles is directly proportional to the Kelvin temperature. So it says as you raise the temperature of a gas, the average speed of the particles increases, but not all the gas particles are moving at the same speed. And this has to do with the molar mass of the gas particles. So if we look over here to this graph, we see that we have several different gases, which are graphed according to the relative number of molecules with an indicated velocity and the molecular velocity of those molecules. So if we look at O2, we know O2's molar mass is 32 grams per mole, whereas H2O is about 18 grams per mole. And so what we see is that the average or the molecular velocity for O2 is much less than the molecular velocity for water, and that's because O2 has a greater mass than water. So back over here in the list, it says argon and helium can have the same kinetic energy, but since helium is lighter, it will move faster than argon, and this is why. Look at the kinetic energy formula. So this is probably the formula you'll see with physics or anything like that. Is kinetic energy is equal to 1/2 the mass times the velocity squared. And so if you have a greater mass, that means you're going to have a lower velocity. Or if you have a lower mass, that means you're going to have a greater velocity. And so even though your mass and velocity of particles may be different, your average kinetic energy can still be the same. But when we're talking about gases, we're talking about this at a certain temperature. And so when we're talking about this, we have to talk about it at a certain temperature. And so we use this formula for the kinetic molecular theory of gases. And so we want to make sure that we include temperature in our kinetic molecular theory. So this would be the formula that if we wanted to find the kinetic energy of a certain gas, we can use that formula. Now, the second postulate we're going to look kind of deeper into is the collision of one particle with another, or the walls of its container, is completely elastic. So what elastic means is that when two particles collide, they may exchange energy, but there is no overall loss of energy. Okay, so when they collide, they may exchange energy, but there's not going to be an overall loss of energy to the environment. So here we have two examples. We have an elastic collision would be like two pool balls colliding with each other, whereas an inelastic collision may be two clay balls colliding with each other. So when two pool balls collide with each other, they just go off in opposite directions. So any kinetic energy lost by one particle is completely gained by the other. There's no loss of energy to the environment, but with the clay balls, they may hit each other. You see that there's going to be a loss of energy to the environment in an elastic collision. So because the gas particles are constantly moving, they strike the sides of the container with a force. The result of many particles in a gas sample exerting forces of surfaces around them is a constant pressure. So the force of all of these gas particles exerting itself on the surface of around them, or the surface of the container, is going to add up to the constant pressure. All right, so let's look at the kinetic molecular theory and the different gas laws that we learned last class. So the first one is kinetic molecular theory and Boyle's law. So Boyle's law states that the volume of a gas is inversely proportional to the pressure. So that means that decreasing the volume forces the molecules into a smaller space. So what we're looking at here with kinetic molecular theory and these different laws is we're looking at what do these particles actually do. And so here with Boyle's law, decreasing the volume, how does that affect the actual particles? The molecules are forced into a smaller space. So more molecules would collide with the container at any one instant, increasing the pressure. So that is how it affects the pressure. So basically this just kind of explains, again, microscopically of what is going on. Now Charles' law states that the volume of gas is directly proportional to the absolute temperature. According to kinetic molecular theory, when we increase the temperature of gas, the average speed, and thus the average kinetic energy of the particles, increases. Therefore, the greater volume spreads the collisions out over a greater surface area, and so that the pressure is unchanged. And so that's how Charles' law, remember, has to do with volume and temperature, applies. Now, Avogadro's law has to do with volume and number of moles. So Avogadro's law states that the volume of a gas is directly proportional to the number of gas molecules. So remember what the mole is. A mole is just a way we can count molecules. Increasing the number of gas molecules causes more of them to hit the wall at the same time. And so what happens is when we increase the number of molecules in a container, then obviously more molecules are hitting the wall. And so if we want to keep the pressure constant, we have to increase the volume. Now Dalton's law is partial pressures, meaning that the total pressure of a gas is a mixture of the sum of the partial pressures. So according to kinetic molecular theory, the particles have negligible size and they do not interact. Particles of different masses have the same average kinetic energy at a given temperature. And so because the average kinetic energy is the same, the total pressure of the collisions is the same. So remember, even though they may be moving at different speeds, their average kinetic energy could be the same, therefore the pressure is going to be the same. Now, when relating this to the ideal gas law, if all of these are true, then kinetic molecular theory is a quantitative model that implies 2PV equals nRT. So basically what this means is that we can apply kinetic molecular theory to every part of the ideal gas law. Now, root mean square velocity. So root mean square velocity is basically how we find the velocity of all the particles together, hence mean, okay? Mean meaning average. So where, and then this is, you may hear it as ERMS, so a lot of people call it ERMS, but where root mean square velocity is the average velocity of all the particles in the container. Now, when we're talking about average velocity of all the particles in the container, we're talking about energy. So if you remember me last class, I talked about how we may use this R when we're talking about energy. This is where we'll use this R. So again, we are going to use this R when kinetic energy equals 3/2 RT. This R is going to be that R because we're looking at energy in joules. And so instead of using that 0.0821, we're going to use this 8.314 as our R in our ohms because we're talking about the velocity. We're talking about energy. And so it has to be in joules. And then the temperature is in Kelvin, and M is the molar mass. And notice it says kilograms per mole. So make sure it's in kilograms per mole. There is one question on your homework that has to do with root mean square velocity. I did not see any questions that you have to calculate root mean square velocity on the AP exam, but I just gave you one on your homework just in case you needed to know how to calculate that. It's pretty straightforward. You plug in that R, you plug in the temperature at Kelvin, you plug in the molar mass, and that will give you the average velocity of all the particles in the container. Now, the last thing I want to look at is the temperature of a gas and the distribution of the molecules. So as the temperature of a gas sample increases, the velocity distribution of the molecules shifts towards a higher velocity. So what this shows is that as I'm increasing the temperature, I have more molecules that are in a higher velocity. And so basically that means that all of my molecules are spread out over a higher velocity, resulting in more molecules with a faster speed. So again, higher temperature gives you more energy. More energy put in the system are particles that absorb the higher speeds or absorb the energy, and so there are more molecules at higher speeds. And so this is the end of kinetic molecular theory. It's fairly straightforward. It's just describing what the particles actually look like within a gas and these gas laws.